Hello everybody and welcome to Enapter's H2 for Engines Various Paths from Fuel to Mobility forum. I'm your moderator for the day. I'm David Hodari. I'm a reporter at the Wall Street Journal and I cover all types of energy from the oldest fossil fuels to the newest and most technologically innovative green fuels such as hydrogen. Thank you for taking part in the poll just now. It was really interesting to see quite how optimistic this audience is about hydrogen's place in the mainstream personal transportation market and indeed the non-personal transportation market as well. Without further ado, I would like to bring on stage our panel participants for the day, or for the session anyway. First of all, I'd like to bring on, if that's possible, Stephanie, Ricard Warnat, who is the operations manager of the Forze hydrogen racing team. Hi, Ricarda. So Ricarda graduated from her BSc in aerospace last summer, and before starting her master's degree, she joined Forze Hydrogen Racing, which is the world's first hydrogen racing team, which is a student team for the Netherlands developing hydrogen electric race cars. And she wants to draw the public's attention to green hydrogen. She's one of the few women on that team, and she wants to inspire more women to join the engineering field. And in 2019, before the pandemic, Forze Hydrogen became the first hydrogen electric race car team to compete in an official race against petrol cars and earn a podium finish. Hello, Ricarda.
Good morning.
Next, I would like to bring in Robin Zalwert, who is the business manager in the funding and legislation department at Keyou, which is a hydrogen tech developer. His work has involved converting diesel and gas engines for use with hydrogen. He also works with regulatory aspects of hydrogen as well as with the public funding aspect of that particular energy field. Some of his work has involved retrofitting engines so they can be repurposed instead of wasted for use with hydrogen. Keyou is building a hydrogen internal combustion engine for cars as opposed to a fuel cell. And the company helps develop hydrogen technologies, combustion processes, and specific hydrogen components for engines and vehicle manufacturers. Hello, Robin. And finally, but not least, Matt Handy, who leads Steamology, which develops a technology that uses steam produced from hydrogen and oxygen to drive a turbine and produce mechanical motion. Matt's also been a project manager with the successful British land speed world record breaking team and has worked on projects across the rail, aircraft, car and bike industries. And Steamology now delivers solutions related to industrial steam heat and power, eliminating emissions, replacing fossil fuels and fossil fuel engines. Hello, Matt.
Hello.
Okay, now that we are off and running, I would like to move to our speaker introductions. So I believe Ricard is up first. Ricard, would you like to take us through your slideshow and tell us why you're here and why you are passionate about hydrogen in the transportation sector?
I would love to. All right. Good morning, everyone. As mentioned, I'm Ricarda. I am the operations manager at Forze Hydrogen Racing. We're a team of 60 students from the TU Delft, many of whom give their studies up for a year, mainly between their bachelor's and their master's. We don't get paid or receive any study credit for this. And with the team, we design, build, and race the world's fastest hydrogen electric race cars. You might be asking yourself, why do we do this? It's because we really do believe that hydrogen is the fuel of the future and that we need an alternative to fossil fuels because the world is obviously warming up and the climate is changing. And if we go on like this, the future generations won't have a world to live on. And because renewable energies are an amazing idea, but the sun doesn't always shine and the wind doesn't always blow, we believe that with hydrogen, we can store a lot of the green energy that is being produced in the form of hydrogen. So a little bit about our history. In 2007, our team was founded because our founder, his name was Edgar van Os, he heard about the so-called Formula Zero competition, which was a conglomeration of a lot of university student teams who were gonna make the first hydrogen racing series, so to say. This is also where our name comes from. Formula Zero is Forze, which I think is a nice little fun fact. And back then they built the Forze 1, which you can see all the way to the left. And it was pretty impressive that that we managed to build such a fuel cell vehicle back in the days, because hydrogen wasn't really explored all that much as a fuel. We then continued to compete in this Formula Zero competition until it unfortunately had to stop due to financial reasons in 2010. Which is when we decided that we wanted to go a little bit bigger. So we decided to start competing in the Formula Student UK competitions, which is the two green cars, the Forze 4 and the Forze 5, which you see on the left as well. It's held annually in Silverstone, and we achieved quite some impressive results, but we kind of decided that we wanted to go even bigger, so we decided to build the Forze 6, which you see on the right-hand side in blue. It was the first actual race car that ran on a fuel cell, with which we set a Nürburgring lap record, which is pretty exciting in my opinion. After that, we kind of decided we wanted to go even bigger, so we started building LMP-based hydrogen race cars. We started out with the Forze 7, which isn't pictured, but in the pictures here you see the Forze 8, which is, as David already mentioned, the car that we competed with in the Supercar Challenge at the Hammer Racing Days in Austin in 2019, where we came second in the sports class, which is obviously pretty impressive that a student team, in my opinion, it's pretty impressive that a student team kind of came second place against actual petrol-powered cars. And now we're looking into the future. We're currently in the process of building our newest car, the Forze 9, which is going to have 240 kilowatts of fuel cell power and boast a double fuel cell system, and it's going to be all-wheel drive. And with that, we hope to participate in the GT class kind of racing, Porsches, Lamborghinis, and the likes. And our mission is really just to show the world that hydrogen is the fuel of the future, and that it's our most promising energy storage going forward into the future. So thank you.
I am so sorry, Robin, but your microphone I don't think is working. I hate to interrupt what I'm sure is a fascinating presentation, but I'm not sure it's one that the audience can hear. Is everything okay with your microphone? I'm afraid I can't hear you. I tell you what, while Robin is figuring that out, why don't we move to Matt Candy's presentation, and we could always ask Robin a couple of specific questions afterwards, just to give him a bit of time to figure things out. I'm so sorry, Robin. Here's Matt.
Great. Can you hear me?
Loud and clear.
Perfect. Thank you. Hello. So my name is Matt Candy, and I'd like to introduce you to Steamology. 10 years ago, the Steamology team broke the world land speed record for a steam-powered car, and the project gave us experience in high pressure and high temperature steam and steam turbines. We broke the record, but we did not smash the record. And so 6 years ago, we started to take a new approach for zero emission power. The combustion of hydrogen and oxygen creates clean green steam. There is no carbon, no NOx, no SOx or particulate. The only product of combustion is hot steam. We're transforming water into power, and this is at the heart of everything we do. We know that renewable energy is plentiful, but it's intermittent. 10,000 times more solar energy strikes the earth every day than we use, and it's free. Renewable energy can be used to power electrolysis, and electrolysis creates both hydrogen and oxygen gas. The gas is collected, compressed, and stored in tanks. And these gas tanks are the battery, the energy storage of our system, so that when the sun has gone down or the wind stops blowing, energy is demanded, gas is combusted in our steam generator, the steam delivers power, and water is produced that can be returned for electrolysis. We have three product groups that share the same common core technology. The first is gas to steam. So stored gas is used to generate steam with a number of industrial process applications, and zero emission steam is generated within seconds at a wide range of quality and quantities. This can be used for distilleries, or pure steam can be used for pharmaceuticals. Saturated steam can provide zero emission heating up to 250 degrees C for thermal oil heating. This is replacing gas or heavy fuel oil burners for continuous or intermittent medium grade heating. The second group is gas to power, and here stored gas is used to generate steam to drive a turbine. And this is diesel engine replacement from 250 kilowatts to the megawatt scale. The steam turbine can provide hydraulic, mechanical, or electrical power, or a combination of these. And Steamology technology is quiet and does not use rare or toxic materials. It's fully recyclable at the end of life. Gas to power markets include transport and static applications, and we've been developing high power steam turbines for industries facing imminent decarbonisation regulation, such as trains, trucks, and ships. Compared to hydrogen fuel cells, we have three distinct advantages for high power applications: much more energy dense, much longer life, and much more cost effective. The third product group is renewable energy storage and electrical generation for on and off-grid applications. So we have facilities near Salisbury in Hampshire in the UK. You're really welcome to come and see our zero-emission high-power turbine demonstrations. Here's pictured in the test cell. And we're looking for industrial demonstrator and commercial sales. So thanks for listening. My name's Matt Candy, and do let me know if you've got any questions. So together we can make green power make a difference.
Thanks, Matt. Thanks very much, Matt. I think without further ado, we'll now move to the broader question to all of our panel. If we could bring all of them back on stage, and hopefully Robin's managed to sort out his microphone bug. Any sign of Robin? Also, Ricardo, if you'd like to unmute your microphone, that would be great as well. Thank you. Okay, I'm not seeing Robin here, but I think we should probably crack on. This is to whichever of you would like to answer the question first. I'm interested to hear about where you see your technologies being applied beyond their current applications. So perhaps maybe Ricardo first, because I mean you've been working with racing cars. I was very impressed by the way to hear you broke the Nürburgring speed record, which is very cool indeed. It's often the case that technologies in regular Formula One and regular racing are applied elsewhere and eventually make their way into other forms of transportation. Do you see the same thing happening with your cars?
Absolutely. So I think that especially because our fuel cell system is quite scalable, we can see it in the Forze 9 that I spoke about, because we do have a double balance of plant system, and we're kind of adding the first one first and then the second one. So it's very scalable and you can kind of apply it to honestly everything. We can see, I'm obviously very interested in aerospace applications, and we can see that Airbus is working on a fuel cell airplane, the 0E. They also have a pretty cool partnership with Eldinklinger, who supplies their fuel cell stacks, who coincidentally also supplies our fuel cell stacks. So, I mean, if it works in our car, it certainly will work in their airplanes. Another application where I really do see fuel cells working is in ports, for example. We're obviously based in the Netherlands, very close to the port of Rotterdam. And one of our previous team members founded a company called ZEP Solutions that makes forklifts for ports and stuff. So I think that's definitely a very interesting application that that we're going to see in the near future. And I mean, it exists already, like the forklifts exist. So I think that's definitely something that we're going to see very soon.
Well, welcome back, Robin. Can you give us a testing 1, 2, 3?
Let's see, 1, 2, 3. Can you hear
there
me?
You are. Fantastic.
Yeah.
Excellent.
Perfect.
So
Nice to
just
be
for the benefit of the audience, I'm so sorry that we had to curtail your presentation, but such are the tribulations of hosting panels in the age of the coronavirus. So maybe you could just, in a couple of sentences, give us a very brief overview.
Okay, I just half the whole thing. Do you want to show the presentation, or should I just quickly explain?
I think you can just tell us if you can just explain.
Oh, okay, cool. So what I was just showing is that our founders from Keyou, they started in the 2000s to work on the hydrogen combustion engine, also fuel cells, and they were working for BMW and MAN. By the end of the 2000s, 2008 actually, there was the financial crisis. They decided to drop the whole topic, and our founders were very, very sad that they couldn't continue their hydrogen projects, and they left the company. In 2015, we started Keyou. It was the right time, let's say, again, and we went for the heavy-duty vehicles. Now, you saw the engine before, maybe there was blue parts, and the blue parts are basically our components. What we do is we take a diesel engine, we exchange some components to hydrogen components, we adapt the engine operation strategy, the combustion process, and then voila, you have a hydrogen combustion engine coming out. And we are selling this whole, let's say, engineering service as well as the components to original equipment manufacturers. That means to engine and vehicle manufacturers. That was the wrap up.
And that was great. That was very pithy. For the ignorant among us, namely myself, how does your hydrogen combustion engine differ in terms of how it works and its benefits from, say, a hydrogen fuel cell?
Mm-hmm. Well, there we go in the comparison straight away. So basically, how a hydrogen combustion engine works, let's call it a hydrogen engine. Hydrogen combustion engine is such a long word. Hydrogen engine is the same as a gas engine, meaning like, for example, natural gas engine. The hydrogen explodes in the chamber and you have the engine running, same as diesel or natural gas. The tricky part is how to burn hydrogen. It's a very, very high flame velocity. It's difficult to control, and the whole, let's say, simulations dynamics of the diesel engines before they don't work on hydrogen combustion. So this is basically our know-how, how to control the hydrogen in the engine. And why is it, where do we see our applications? Our application is basically that we see that fuel cells, they're working, but they're still very expensive. And they're not here yet in serious production. And you could say we might be a bridge technology. Some argue against it, but the heavier the vehicle becomes, the less people see us as a bridge technology. But for the moment, we can just take our components, throw them at the value chain of the diesel engine value chain, and they can start producing hydrogen combustion engines straight away from serious production. Additionally, for vehicles that go for a very long time, like for example trains or ships, you can take the old one out and put the new one in, and you have a very, let's say, sustainable way of continuing to have mobility with zero emissions.
Got you. That's really interesting. Matt, I'm so sorry to leave you neglected in the corner there. Perhaps you could talk to us a little bit about where you see. So we've gone from Robin's hydrogen combustion engine to Matt's hydrogen steam turbine. You know, where does that differ from Robin's, and where do those applications differ as well?
Yeah, well, I think there's going to be lots of niches in the future, and it's looking at the range of power output. So we concur with Robin. You can't do a direct mechanical drive with a fuel cell. So for retractioning or repowering of vessels, trains and trucks using conventional gearboxes, I think Robin and I are in the same camp. So we're looking at trains and trucks and ships where you can come out with the same mechanical output. So you can have a very spanner friendly, simple materials, long life, easily recyclable, and in a closed system that's robust to the environment. And also we're temperature agnostic. I think we'd share that with Robin. So at cold temperatures, batteries struggle. At hot temperatures, fuel cells struggle. Both the internal combustion engine and the steam turbine agnostic to temperature. So we've then got a very energy dense platform. And yes, we could do a car or a van or a truck. But that's being well served by batteries and fuel cells. We're focusing our beachhead market at 250 kilowatts to the megawatt, where the turbine maintains a very similar size. We're just adding more steam generators. So we've got a very compact engine, and everybody is chasing range because of these gaseous fuel projects. The fuel tank is literally the elephant in the room, and we're used to very compact, energy dense fuel sources. So by having a small engine of reasonable efficiency over a wide range of temperatures, we leave room for the fuel, and that's where we come in. We're interested in this space up to the low megawatts for these transport applications in the first instance.
Fascinating. And at the risk of asking a vague question, but this is to any and all of you who want to answer this, what would success for your respective companies look like? Now, I'm sure you're feeling very successful already. You're here on this esteemed panel, but 5 years from now, where would you like your companies to be?
I think I'll go first. So I think for Forze, it would be amazing for us, obviously, to actually win a race. We've come second, but we want to win a race. We kind of want to prove to people that there is a future for hydrogen in racing, possibly even Formula One. Who knows? I think that would be definitely a quest, not necessarily for us, but I think that would be very nice to see see as an application for hydrogen as well, and definitely winning races and kind of working our way up into higher classes than even the GT class.
Should I continue or you want to go, Matt?
Carry on, yeah.
Okay. I think there's two successes. Success from the entrepreneurship view would be that every engine in the world is going to have a Keyou stamp on it, Keyou inside, and there's our technology enabling the engine to run on hydrogen. That would be the dream of our founders. If I go to our engineers, they don't care so much about money, I have the feeling. For them, the big dream would be to design a hydrogen combustion engine from scratch. What we are currently doing is we are adapting engines to hydrogen. But our engineers are fantasizing, if you build it from scratch, you can get much higher efficiencies and go way beyond. That would be the big dream for them.
Yeah, I think in the big picture, Steamology has ambitions to be a cradle-to-cradle company. So this is facilitating clean energy to allow abundance, really. We talk a lot about sustainability in the world, and really sustainable sort of just hanging on to a lifestyle that we have, but it's perhaps not so optimistic. But, you know, renewable energy is an external input into the planet. It is plentiful. If we make and design things without toxicity, being kind to water, etc., we can build towards abundance, and that needs energy. But it is there, this 10,000 factor, we can convert it. So we want to be part of that in a clean energy environment to enable. And in the stepping stone of that, we need some commerciality. So in the next few years, we aim to be on some trains.
Fascinating. And I think there's just time to squeeze in one last question to the panel before we proceed to our Q&A section. We've spoken a lot about mobility. That's the raison d'etre of this entire panel. But perhaps you could talk to me a little bit about where you see your technologies being applied outside of the field of transportation, or indeed whether you do see that. It's okay if you don't.
I think a lot of this electricity is key. So we see a lot of parallels. So with the trains, if you can run under the wires, run under the wires. But electrification isn't anywhere. So you need a stopgap, a get you home. And if your last mile's a mile, use batteries. If it's greater, use, we would like to think, our turbines. But we're talking to the steam industry for distillery. So distilleries are very energy intensive, and you can get electric boilers. But you've got this mismatch. When the power is available from renewables, is not when you're brewing. So you need an intermediary. So we're servicing that distillery steam market, pure steam for pharmaceuticals. And it's this combination, and bi-mode is often coming out. So base load on electricity, use other clean energy for storage. And that's in a wide range. We've got a project in Kenya where we're looking at off-grid power.
Interesting. And Robin and Ricard, do you have any non-transportation applications for your technologies, or is it very strictly within the transportation realm?
Please go first, Ricardo.
Okay, no, I actually have an opinion on this. So we have seen fuel cells being used in buildings and stuff, which kind of is similar to what Matt said. So I think that's the main application outside of mobility, really. But I do believe that the main application of fuel cells will stay within the mobility sector, personally.
Yeah, for us, it's we basically went into mobility because this is where our founders are coming from the automotive market, so they know this market. For the moment, we have a very nice competitive advantage over the fuel cell, and this is they are fast and in high quantities, but I think they will catch up at some point, and we're all fighting for hydrogen anyways. But there's very, very nice applications where I don't see the fuel cell, I don't see the battery, for example, in agriculture, all agricultural machinery. With batteries, it's very heavy. It would go on the soil and destroy it. And you need clean air. You need very clean air to run a fuel cell. So there I see very nice potential. And another niche that is ought to explore is the utilization of hydrogen combustion engines with liquid organic hydrogen carriers. Because liquid organic hydrogen carriers, they can release the hydrogen on board, and we don't need a very high quality of purity. So whereas fuel cells would need like a 5.0 purity of hydrogen, we can go with much dirtier hydrogen. So we can use the hydrogen from the LOHC straight away, or also go into residual hydrogen from the alkali industry, for example, which release the hydrogen at a very low quality. So I think we are not in each other's way, but we can go on different paths to the same goal.
Great. And now I think we should probably move on to audience Q&As. So I'm just trying to figure out how this works. Perhaps some audience members with questions could raise their hands, if I'm not mistaken. That might be how it works, unless Stephanie, you would like me to pick questions and answers from the Q&A section of the chat. Okay, I will pick some from the Q&A section of the chat then. There's a question here from Johannes Gulden. I hope I'm not butchering that, which I believe is aimed at Robin, which says, "What is the biggest power engine that Keyou has adapted?"
It's all about how big everything is, right? Now, currently, the biggest engine that we have adapted is a 15-liter engine. It's a truck engine for 40-ton trucks. But we are going towards 20-liter for the moment for stationary applications also. Great.
And there's a fascinating question here from Gabriel Marinho Silva, which is, since hydrogen burns with flames hotter than natural gas, what are the nitrogen oxide emissions related to this process? How can we mitigate them? And also, from a personal point of view, I'm interested to hear about how burning hydrogen in the place of fossil fuels, say in power plants, for example, might also have different effects vis-a-vis emissions.
Okay, first I will answer to Gabriel. I had a jump in your question, David. Maybe you can repeat it, but after I respond to Gabriel's question. So what we do is that we have a high, very high excess oxygen in the burning chamber. I'm not one of the engineers, so I try to explain as good as possible from my side. We have a lambda around 1 to 2. We have a high oxygen excess in the air chamber, in the combustion chamber, which means that the NOx emissions are lower than for the fuel engine, because it's possible to have this ratio of oxygen. We have currently NOx emissions which are about half to 1/3 of what is the legal limit for the Euro 6. And we are currently working on 2 technologies to actually store or get rid of the NOx emissions with oxygen. So we're working on getting sub-zero emissions. That means that the air intake has higher NOxes than the air outtake. But I don't want to say too much to it because it's still in the process, and we're working with the university together, so there's still margin for errors and margins for failure, but we're working on it, let's say.
Sure. I've got a question here for Matt Candy, asking, based on your findings, what top 3 industries would you target for the gas to power market applications of your technology?
Well, I think for gas to power with the turbines, it is this high power. So we've been working in the rail freight industry. They're at 2.4, 3.3 megawatts, and it's been shown that the freight industry want a single cab solution, so that all of the fuel and the engine is on one locomotive. You don't have tenders. If you do it with batteries or fuel cells, you're going to have multiple tenders, which takes up weight, length of the train, very difficult to turn around, very expensive. So the freight train, and because we can do steam electric or mechanical drive, we can retraction existing stock, which has a very long life. So marine, 40 years, rail, 40 years. So the asset has a life far beyond the regulatory use of the current traction. So we're exploring those steam electric, mechanical power, both in bi-mode and in replacement. We'd like to look at the 40-ton truck. About 250 kilowatts, 300 kilowatts is where we come on strong, similar to Robin. And because you don't have to electrify the drivetrain, and you can use existing transmission tech, that's a good space for us to be.
Great. And a couple of questions I'm seeing coming through for Ricard. First of all, is Forze using custom fuel cells? And also, how does the Forze 8 H2 endurance race car differ from competitors in terms of power to weight ratio?
I'll start off with the first question about the fuel cell. So like I mentioned before, we partner with ElringKlinger, and they basically give us some of their fuel cells that aren't on the market yet. So they're not necessarily custom, but they're kind of prototypes, which is also something we kind of use to make an impact, because we sell, or we give them our data that we retrieve from this in order to kind of further their development as well. So I think that's a really nice way of partnering. And then in terms of power to weight ratio, we're not quite there yet, but it would be very interesting to see what professional OEMs like Audi, McLaren, BMW can do with this technology. It's very important, but if you're looking into endurance, it's not the only thing necessarily that's important going to the future.
Sure. And I think we just have time for one last question. And an interesting one that's coming up here seems to be for Robin, asking very briefly, and as though it could be understood by a child, i.e. me, what are the changes we have to make in order to retrofit a diesel engine into a hydrogen engine?
On my slide before, I showed you some components. I don't know which ones you remember. There were 8 components, plus the exhaust aftertreat system, plus the combustion process, plus the operation strategy, and that would be it. What we are changing basically is the ignition system. Mainly all of these big engines are diesel engines, so you have to introduce a ignition module and spark plugs. The injection system is of course different, it's hydrogen. The ECU has to be adapted to hydrogen. The pressure regulation, of course, the valves, the exhaust gas recirculation system, we are also exchanging and adapting it to hydrogen. Additionally, the air charging system, the piston system, and as I said, we're working on an exhaust after treatment system that can get down all the NOxes. And those would be all components that are being changed.
Sure. And seeing as we appear to have reached 12:05 for you, I'm in London. I was wondering if we could return to the poll that we had at the start of the session, which was, when do you see hydrogen application becoming part of the transportation mainstream? And as you can see here, we had, we're starting again, but at the start of the session, we had just under halves showing by 2030, sizable amount of people saying we're already there. And I think about 4% of you being very pessimistic and saying it's not going to happen. But I'm interested to see what the views are, whether your views have changed or whether they haven't. So I'm going to leave you to answer this question for a couple of minutes, and hopefully we can come back and review the answers before the end of the session in about 4 minutes. I think actually while that poll's being answered, perhaps we can take 1 or 2 more questions from from our panelists while our audience clicks on that poll. Let's see what we have here. Matt, what is the difference from the system applied in rockets a long time ago?
Yeah, no, I saw that one. Yes, we are able to say this is rocket science. So yeah, if you know, fundamentally, it's not new. That one of the compelling things is that we've got a very simple continuous combustion, no moving parts in the steam generator. We use a Delaval nozzle to transfer the heat and the pressure of the steam onto an impulse turbine. So it's not like a gas turbine. It's a very simple impulse sort of water wheel turbine using the kinetic energy of high velocity steam. So yeah, typically a steam generator would work as a rocket. You got about half a ton thrust out the back of it. And that's what's imposing onto a very simple, relatively slow turbine. It's only doing 9,000 RPM. And the steam at that point is very low temperature, 110. So we've got a very limited part where you've got the very hot 2,500 degrees C steam. You bring that down with additional water. That doesn't, and we use that to drive the turbine. But in principle, it's no different.
Sure. And in the final sort of just over a minute and a half we have left, it'd be good to review the that poll if we can see the the results of it. Well, while we're waiting for that, here we go. We have a little over half saying that they expect hydrogen-powered vehicles to be part of the personal transportation mainstream by 2030. About 31%, so just under a third, say by 2040, and the remainder say we're already there, not till 2050, or it's not going to happen. To our panelists, before we go, perhaps you could weigh in on this question as well. Do you have a view?
Yeah, it's an infrastructure piece. I think what we've demonstrated across the board today is the tech is coming there. I think it's an infrastructure piece.
I agree in this sense. And if you look at the national hydrogen strategies that we have, or the European hydrogen strategy, they clearly say until 2025, we want to raise the hydrogen infrastructure so that we have hydrogen available. And from 2025, there will be more focus and funding also for mobility. So in this time period between 2025 and 2030, this is where hydrogen mobility will start rising.
And Ricardo?
Yeah, I couldn't agree more. I think a lot of the reason why we're not there yet is the whole chicken and the egg thing. People always like to say that a lot. Yeah, but I think that a lot of countries are building a lot of hydrogen refueling stations. So I think we're definitely going to get there within the next 5 to 10 years. I can only agree.
Good stuff. Well, to all of you, the panelists, and to our audience, thank you very much for joining us today. I think that just about wraps it up from our end of things. And thank you for joining us.
Thank you.